Number C, a solenoid of radius 5 cm has 200 turns and a length of 15 cm. Calculates inductance. Let's say you have a solenoid here, and the length of the solenoid is 15 centimeter. Number of turns is 200. This is n, and the radius of the solenoid is 5 centimeter. So this is the information given by the question for the solenoid. So when the current flow I in the solenoid, meaning that you have a flux linkage in the solenoid here. So what is the inductance? This is number 1, right? So inductance L is for the solenoid is given by the equation mu naught n square A divided by length of solenoid. So all the, this is mu naught is a constant for pi exponent minus 7, and the n, this number of turn is 200, and so this is a 200 square, right? And the area A, so how to calculate the area A here? Because of the radius is 5, so meaning you must have a convert to the meter is 0.05. okay, this is R, right? This is R, but to calculate the area A is pi R square, so this is value of the R, and the length here is 50 cm, so make sure you use a convert to the meter. So the L, if you use a calculator, is equal to 4 pi exponent minus 7, this time n is 200 square, and the A is equal to 0.05 pi square, right? Square, and divided by length is 0.15. Because of 15 convert to the meter, 0.15 meter. So the value of inductance is equal to 2.6 millihenry. And number 2 is what is the rate at which current must change for its induced EMF 15 millivolt. So for the number 2, you can use the information by relates between EMF and inductance L. So EMF inductor L is equal to L, the rate change of current. So this is the equation or the formula that you can use to calculate the rate change current. So the rate change of current here is a d I dt. So di dt is equal to EMF divided by L. So EMF is 50 milli is times 10 power of minus 3, and the L is a answer number. This is L. This answer from question number 1. So 2.6 is right, milli here is times 10 power of minus 3. So now you can find the di dt here. I write here. So di dt is equal to, so you can use the calculator here. The answer is 19.2 ampere per second. This is number 2. Next question, number D. 2 coaxial coils, one around the same cylindrical core. The primary core has 350 turns. So this is for the primary. So I will look at the, let's say this is a coil, right? Or I draw the solenoid, right? It's like the solenoid here, and the primary coil is turns 350, and we have another coil here. This is secondary is 200. Let's say you have a secondary coil here, so this is 200 turns. When the current in the primary coil is 6, this is primary, right? So 6.5 ampere, this is current, the IP. So meaning we have a flux linkage in the coil 1, right? And the average flux through each turn of secondary coil 0.018 Weber. So meaning the flux produced by the primary coil pass through to the secondary coil is 0.018. So this is flux linkage to the secondary coil. So number one is what is the mutual inductance? So number one is what is mutual inductance. So you can use the equation. Mutual inductance is you can relate between the flux pass through to the secondary coil. Flux. This is flux for the secondary coil into the secondary coil, and number of turn of secondary coil, and divided by current flow for the primary coil. So this is IP. This is 2. Also I use a secondary S, right? This is S, this is primary, this is secondary, and this is number of turn of secondary. So this is how you can find the mutual inductance of the pair of coil. Now the value of the number of turn of secondary coil is 200, and the flux through the secondary coil is 0.018 Weber, and the current flow must refer to the current flow in the primary coil, 6.5 ampere. So the mutual inductance, you can use the calculator, is 0.55 Henry. And number 2, average flux through the each turn of primary coil when the current in the secondary coil is 1.5. So now the current flow in the secondary coil is current flow here is 1.5 ampere. So what is the average flux through, or flux linkage, or average flux through to the primary coil? This is the red color primary coil. Number 2. So still you use the equation. Mutual inductance is this is for the primary, right? So meaning the number of turn of primary, right? And flux through the primary coil, and divided by current flow in the secondary coil, because the answer asks you to the current flow when the current in the secondary coil. So this is IS. So flux, right? This is flux for the primary through the primary coil is equal to M, this is right, time current flow in the secondary coil, and divided by number of turn primary coil. So mutual inductance is answer come from the number 1. This is 0.5 because the mutual inductance between secondary and primary is the same magnitude, and the current flow in the secondary coil is 1.5, and number of turns of primary coil is given 350. So the flux, average flux through each turn of the primary coil, can use the calculator here, is 2.36 exponent minus 3 Weber. Right? Thank you.